Welcome, and tonight we will take a slow and peaceful journey through one of the quiet systems that helps large buildings feel comfortable, balanced, and calm. As you settle in and begin to relax, you can imagine a large building at night. Perhaps it is an office tower after everyone has gone home. Perhaps it is a hospital where only a few lights remain on. Perhaps it is a school, a hotel, or a research facility. From the outside, the building appears still and quiet. Hallways are empty. Doors are closed. Most people are asleep. And yet, deep within the walls, above the ceilings, and inside carefully designed mechanical rooms, a gentle movement continues. Air is still flowing. It moves softly through hidden pathways, guided by fans, ducts, dampers, and controls that work together without drawing attention to themselves. The system does not rush. It does not force anything suddenly. It simply continues, maintaining a steady and reliable rhythm that supports the building hour after hour. Tonight, we will follow that rhythm. We will begin outside the building, where fresh air first enters. We will pass through louvers and filters. We will move into the air handler, where the air is cleaned and conditioned. We will travel through long, quiet ducts and into occupied spaces. We will feel the gentle adjustment of VAV boxes and thermostats, and eventually, we will follow the return air as it makes its calm journey back to the system, completing a continuous loop. There is no need to memorize anything. There is no need to solve any problems. You do not need to understand every detail. You can simply listen. And as you listen, you may begin to notice that HVAC systems are, in many ways, naturally calming to think about. They are designed to create stability. They keep temperatures from drifting too far in either direction. They bring in fresh air. They remove stale air. They guide warmth and coolness exactly where they are needed. They respond gradually to changing conditions, making small adjustments that are often so subtle that the people inside never notice them. A well-designed HVAC system works quietly in the background. Most of the time, the people inside a building are not thinking about air handlers, filters, fans, or ducts. They are simply experiencing the result, a room that feels comfortable, balanced, and steady. And that comfort is created by air. Air that is constantly moving. Air that travels in a carefully controlled loop. Air that enters, is cleaned, is conditioned, is delivered, and then returns again. Over and over. Day after day. Night after night. The journey of air is often long, gentle, and carefully controlled. You might imagine the building now as a living structure that breathes slowly and quietly. Fresh air enters. Conditioned air flows outward. Used air returns. The cycle repeats. Nothing sudden, nothing rushed. Only a steady movement that continues in the background. HVAC systems help large buildings feel stable and comfortable. Commercial HVAC systems are built to serve large spaces, from office towers and hospitals to schools and laboratories. They are designed to manage temperature, airflow, humidity, and ventilation in a smooth and coordinated way. Even though these systems can be large and complex, their purpose is simple: to help the building feel comfortable, to help the air feel fresh, to help temperatures remain steady, to support the people inside without drawing attention to the equipment itself. Air usually moves in a continuous loop through the building. Fresh air enters from outside. Indoor air returns to the system. The two may be mixed together. The air is filtered, heated, or cooled, and sent back out once again. This loop continues quietly, often unnoticed by everyone inside. Commercial HVAC systems often work in the background. They are present, but rarely obvious. A slight movement of air from a ceiling diffuser. A soft hum from a distant mechanical room. A comfortable temperature that remains steady throughout the day. These small details are signs of a system doing exactly what it was designed to do. A well-tuned HVAC system supports comfort with very little effort from the people inside the building. Thermostats monitor conditions. Controls make adjustments. Fans maintain airflow. Dampers open and close gradually. Pumps move water through equipment. And all of these parts work together to maintain balance. You can think of the system as a quiet caretaker, always present, always adjusting, always moving air gently from one place to another. And as you continue to listen, you may begin to notice how naturally calming this process feels. The movement of air is smooth. The changes are gradual. The purpose is comfort. And the result is a building that feels stable, balanced, and easy to be in. Now, in your mind, imagine standing outside a large commercial building at night. The sky is dark and still. The parking lot is quiet. Only a few lights remain on inside. From the outside, the building appears almost motionless, and yet the HVAC system continues to operate. Somewhere near the roof or along an exterior wall, fresh outside air is entering the building. This is where our journey begins. Outside, air enters the building through carefully designed intake openings. These openings are placed where they can draw in clean outdoor air while protecting the system from unwanted debris and weather. Covering many of these openings are louvers. Louvers are angled metal blades that help shield the intake from rain, leaves, and debris. They also help guide the incoming air smoothly into the mechanical system. Even at this first step, the movement is controlled and deliberate. The air does not rush. It is guided gently inward. Fresh air often enters a mechanical space before it enters the occupied parts of the building. There, it may pass through dampers. These dampers control how much outside air is allowed to enter. On some nights, more fresh air is needed. At other times, only a small amount is required. The dampers adjust slowly and quietly, maintaining the right balance. And so, with calm and steady motion, the outside air begins its journey into the building. As the fresh outside air passes through the intake openings and beyond the louvers, it continues deeper into the mechanical space, where the next quiet stage of its journey begins. Before this air can move through the building, it is gently cleaned. Filters help remove dust, pollen, and other small particles carried in from the outside world. They do their work silently, catching what does not belong and allowing cleaner air to continue onward. The process is simple and steady. Air approaches the filter. Tiny particles are held back. Cleaner air passes through. And because the air is cleaner, it can move more easily through the system. Clean filters help airflow more freely. They reduce resistance and help the equipment work with less effort. When filters are maintained regularly, the entire HVAC system tends to run more smoothly and quietly. You can imagine the air now becoming lighter and clearer as it moves beyond the filters. The journey continues toward one of the most important pieces of equipment in the building: the air handler. The air handler is often the main point where air is managed. This large piece of equipment is designed to move, clean, and condition air before it is distributed throughout the building. In many ways, the air handler acts as the lungs of the building, drawing air in, preparing it carefully, and sending it back out again. Inside the air handler, many components work together. Filters continue their quiet task. Dampers regulate airflow. Coils adjust temperature. Sensors monitor conditions. And at the center of it all, fans provide the motion that keeps the entire system alive. Fans inside the air handler create the pressure needed for airflow. The fan gives the air steady motion, not a sudden burst, not a forceful push, just a smooth and continuous movement that carries the air forward. As the fan turns, the air begins to move with purpose. The flow is organized and controlled. Every turn of the fan helps maintain a gentle pressure difference that guides the air into the next stage of its journey. Before leaving the air handler, the air may pass across heating or cooling coils. These coils quietly change the air temperature. If the building needs cooling, the coils remove heat from the air. If the building needs heating, the coils add warmth. The transformation is gradual. The air enters one temperature and leaves another, more suited to the comfort of the spaces ahead. Coils transfer heat between air and water or refrigerant. This exchange happens continuously and without drama. Heat moves from warmer areas to cooler ones, and the air is prepared to support a comfortable indoor environment. In larger buildings, chillers often provide the cooling energy needed by these coils. A chiller removes heat from water or refrigerant, allowing the system to cool the air effectively. The heat that is removed may eventually be carried to a cooling tower, where it is released into the outside air. Boilers are often used when warmth is needed. They create hot water or steam, which can circulate through coils and transfer gentle heat to the moving air. Pumps move this water through pipes and equipment. They maintain a quiet circulation of thermal energy, carrying warmth or coolness to exactly where it is required. Heat exchangers allow energy to move efficiently from one place to another. One fluid gives up heat, another receives it, and the air continues on, changed but still moving steadily. Inside the air handler, everything works together in an organized loop. Outside air has been cleaned. Temperature has been adjusted. The fan has created motion. The air is now ready to travel, prepared carefully, balanced precisely, moving calmly. The air handler keeps air moving in an organized loop. It receives air from outside and from the building itself. It filters and conditions that air. Then it sends the air onward into a network of hidden pathways. The building, in a sense, has taken a slow and measured breath. Fresh air has entered. It has been cleaned. It has been warmed or cooled. And now, with steady pressure and quiet momentum, the conditioned air begins to leave the air handler. Ahead lies a vast system of ducts stretching above ceilings and through walls, long metallic pathways, carefully sized and carefully arranged, silent routes that carry air to every corner of the building. And so, with the gentle turning of the fan and the soft guidance of the air handler, the conditioned air begins its quiet journey into the ductwork. As the conditioned air leaves the air handler, it enters a hidden network that extends throughout the building. These are the ducts. Ducts act like quiet pathways for moving air from place to place. Most people rarely see them. They are tucked above ceilings, behind walls, and within shafts that connect one floor to another. And yet, they are always there, carrying air patiently and continuously. The duct system can be thought of as a circulatory network. Instead of carrying blood, it carries air. Instead of reaching organs, it reaches offices, patient rooms, classrooms, conference rooms, and hallways. Each duct has been carefully sized to carry just the right amount of airflow. If a duct is too small, the air may move too quickly and create noise. If a duct is too large, the system may become inefficient. When the duct is sized correctly, the air moves with less resistance and with less sound. Air moves best when ducts are clear and properly sized. A well-designed duct system allows the air to travel smoothly through many turns and branches. At first, the air may move through large main ducts. These large pathways carry substantial amounts of conditioned air from the central equipment to different areas of the building. As the air travels farther, the ducts often become smaller. Large trunks divide into medium-sized branches. Medium-sized branches divide into smaller branches. And smaller branches lead to individual zones and rooms. The journey is orderly. The airflow is divided carefully. Each branch receives only the amount of air it needs. Supply ducts bring conditioned air to occupied spaces. These ducts carry air that has already been filtered and adjusted to the proper temperature. The air may be slightly cooler than the room during summer. It may be slightly warmer during winter. But in either case, it travels quietly toward the spaces where people live and work. As the air moves, it encounters bends, transitions, dampers, and control devices. Each component guides the flow. Each component helps maintain balance. And still, the air continues, steady, organized, unhurried. Some parts of the building may be close to the mechanical room. Other parts may be many floors away, yet the duct system reaches them all. Air can travel above a quiet office corridor, behind the walls of a hospital, or through the ceiling of a school after everyone has gone home. The movement is usually unnoticed, but it never fully stops. Lower air speed often means less noise. This is one reason why well-designed HVAC systems feel so calm. When air moves at a moderate pace, it can deliver comfort without drawing attention to itself. Instead of a rushing sound, there may only be a faint whisper of air at a diffuser, a soft and steady presence. Well-designed ducts help air move with less sound, The shape of the ductwork matters. Smooth transitions reduce turbulence. Gentle turns allow air to keep moving evenly. Balanced pathways prevent sudden pressure changes. Each design choice contributes to quiet operation. As the conditioned air continues through the duct system, it approaches another important device, the VAV box. In many commercial buildings, the duct system does not deliver the same amount of air to every space at all times. Different rooms have different needs. A sunny conference room may require more cooling. A small office with one occupant may need less. A hallway may need only a modest amount of airflow. To respond to these changing conditions, the building often uses variable air volume systems. VAV systems adjust airflow to match demand. Rather than turning the airflow fully on or fully off, they make gradual adjustments. A little more air when needed, a little less when conditions become comfortable. This quiet flexibility helps the building remain balanced. And so the air continues through the ductwork, moving toward the VAV boxes that will gently decide how much of that air each part of the building will receive. The conditioned air arrives at the VAV box with the same calm momentum it has carried since leaving the air handler. VAV stands for Variable Air Volume. The name describes exactly what the device does. It changes the volume of air delivered to each space. Not suddenly, not dramatically, but gradually and with quiet precision. A VAV box is usually located above the ceiling, hidden from view. Most people in the room below never realize it is there, and yet it plays an important role in maintaining comfort. It listens to the needs of the space. It receives information from thermostats and control systems, and it adjusts airflow accordingly. In many buildings, VAV boxes control how much air enters each zone. A zone is simply an area that can be managed somewhat independently from the rest of the building. One office may need more cooling. Another room may already be comfortable. A conference room filled with people may generate extra heat. A storage room may need very little airflow at all. The VAV box responds to these differences. A VAV box can open wider when a room needs more air. When the room warms and the thermostat senses a change, the control damper inside the VAV box gradually opens. This allows more conditioned air to pass through. The increase is smooth and measured. More air enters the space. More cooling or ventilation is provided, and the room slowly returns to a comfortable condition. A VAV box can close partway when a room needs less air. When the room becomes comfortable, the damper begins to close. Not completely in most cases, just enough to reduce airflow to what is actually needed. This helps the building stay comfortable without wasting energy. Instead of sending maximum airflow everywhere at all times, the system sends only what each zone requires. Some areas can receive more air, others can receive less, and each space receives what it needs in that particular moment. This is one of the quiet efficiencies of commercial HVAC systems. Comfort is maintained through small adjustments, tiny movements of dampers, slight changes in airflow, gentle responses to changing conditions. The people inside may notice only that the room feels steady. The thermostat helps guide these adjustments. Thermostats tell the system when heating or cooling is needed. They compare the current room temperature to the desired set point. If the room drifts warmer or cooler than intended, they send a signal to the control system. The response is typically gradual. There is no need for abrupt changes, only a quiet correction, a return toward balance. Some VAV boxes also contain heating elements or hot water coils. These devices can add warmth when needed, especially in perimeter zones near exterior walls and windows. On cool mornings, the air may arrive slightly warmer. The room becomes comfortable again, and the transition often happens so slowly that no one notices. After the VAV box adjusts the airflow, the conditioned air continues its journey. It passes through short branch ducts toward diffusers and ceiling outlets. The path is now very close to the occupied space. The air has traveled from the outside world, through louvers, through filters, through the air handler, across coils, through fans, along ducts, and through the careful control of the VAV box. Each step has been deliberate. Each adjustment has been gentle. Each movement has been part of a larger and well-organized system. Soon, the air will enter the room itself. It will spread softly through diffusers. It will mix with the existing room air. It will carry warmth or coolness exactly where it is needed. And in doing so, it will help create the quiet sense of comfort that people experience every day, often without realizing how thoughtfully that comfort has been delivered. And so, with its volume carefully adjusted and its path clearly defined, the conditioned air moves onward toward the ceiling diffusers, ready to enter the room in a soft and even way. The conditioned air, having passed through the careful adjustments of the VAV box, now moves into the final stretch of its outward journey. It travels through short branch ducts, narrow and purposeful, leading it toward the last opening before the room itself. That opening is the diffuser. Diffusers are quiet, unassuming devices. They sit in ceilings and walls, often designed to blend with their surroundings so completely that most people never give them a second thought. And yet they play a meaningful role in how a room feels. They are the final point of delivery, the place where all the careful work of the HVAC system meets the space it was designed to serve. Supply air is usually delivered through diffusers or ceiling outlets. A diffuser does exactly what its name suggests. It diffuses. It takes the air arriving through the duct and spreads it gently across the room, rather than allowing it to enter in a concentrated stream. Without a diffuser, air might blow directly down onto a desk or a chair, creating an uncomfortable draft. With one, the air fans out softly in multiple directions, dispersing across a wider area before it reaches the people below. The shape and size of a diffuser affects the way air moves into the room. Some diffusers are round, casting air outward in a circular pattern. Others are long and rectangular, spreading air in two directions along the length of a ceiling. Still others are designed to throw air at a low angle, keeping it close to the ceiling before it gradually descends. In each case, the goal is the same: gentle, even, unobtrusive delivery. Diffusers spread the air softly across the room. You might imagine lying in a quiet office after hours. The lights are dim. The room is still. And above you, from a simple white grill in the ceiling, a barely perceptible breath of air is entering the room. It fans outward across the ceiling, gradually mixing with everything already there. If you held your hand up toward it, you might feel only the slightest movement of air, a whisper of coolness, or perhaps warmth, depending on the season. That gentle presence is the result of a great deal of careful design. Engineers choose diffusers based on the size of the room, the height of the ceiling, the amount of air that needs to be delivered, and the distance the air needs to travel before it reaches the people inside. Too much air from too small a diffuser creates noise and discomfort. Too little air from too large a diffuser fails to mix the room properly. When the selection is right, the diffuser works almost invisibly. Supply air comes out into the room with care. The air leaving the diffuser is typically moving at a moderate pace. Not still, but not rushing either. It enters the room with enough energy to spread and mix, but gently enough that it causes no disruption. It carries within it the conditioned qualities that the HVAC system worked to create: the right temperature, the right humidity, the freshness of filtered air. And as it spreads across the room, it begins its next task. Not the task of traveling through ducts or navigating dampers or passing through coils. Its next task is simpler and in some ways more intimate. It is the task of mixing with the air already present in the room, slowly and naturally becoming part of the space it has entered. Clear vents help air reach rooms more evenly. When diffusers are unobstructed, the air can spread as designed. Furniture arranged away from vents, ceilings kept clean and unblocked. These small details help the system work as intended. The air finds its way evenly across the room, without pockets of stillness or unexpected drafts. In a large building, dozens or perhaps hundreds of diffusers may be working at the same time, each one quietly completing its small part of a much larger system, each one delivering, in its own gentle way, the conditioned air that helps the building feel comfortable. And so, the supply air arrives. It enters the room with soft, even motion. It spreads across the ceiling. It begins to descend gradually into the space below, and it begins to interact with the room around it, becoming part of the building's quiet indoor environment. The air has traveled far to reach this moment, and its work in the room is only just beginning. The supply air has entered the room. It has spread softly from the diffuser, fanning outward across the ceiling, before beginning its gradual descent into the space below. But the work of the HVAC system does not end at the moment of delivery. What happens next, inside the room itself, is equally important to the comfort of the people within it. The supply air mixes gently with the room air. This mixing is not forceful. It does not happen in an instant. It is a slow and gradual blending, driven by the natural movement of air and the gentle momentum provided by the diffuser above. The cooler or warmer supply air encounters the existing air in the room, and the two begin to find a common state, slowly and continuously. Think of it like two different temperature bodies of water meeting in a still pool. One slightly cooler, one slightly warmer. Over time, and with even the gentlest current, they blend. The boundary between them softens. A new, more even temperature emerges. Room air behaves in a similar way. The supply air descends through the room, driven by its own temperature and density. Cool air is slightly denser than warm air, so supply air delivered for cooling tends to sink slowly toward the floor. Warm air is lighter, so heating supply tends to rise and spread from above. In either case, the movement is gradual, and the mixing happens over the course of minutes, not seconds. As the air gives up heat or picks up heat, it changes. This is the heart of what happens in the room. The supply air arrives with a purpose: to bring the room toward a desired temperature. It does this by exchanging heat with the air and surfaces around it. If the room is warm and the supply air is cooler, the supply air absorbs some of that warmth. If the room is cool and the supply air is warmer, the supply air releases its heat into the space. The transfer is gentle and continuous. As the supply air mixes and changes, the room slowly drifts toward the temperature the thermostat was designed to maintain. This drift is rarely abrupt. It is measured in fractions of a degree at a time. A room that is slightly too warm becomes, over several minutes, a room that is comfortable. And then the supply air adjusts, reducing its cooling contribution once the target is reached. Good airflow helps temperature stay even across large spaces. In a small room, one diffuser may be enough to accomplish this mixing on its own. In a large open office, many diffusers work together, each one contributing to the overall movement and blending of air. Their combined effect creates a gentle indoor current, too soft to be felt as a breeze, but sufficient to prevent any one corner of the room from becoming stagnant or uneven. This is one of the quiet achievements of a well-designed HVAC system. The temperature in a large room can remain remarkably consistent from one side to the other, not because the building controls every molecule of air individually, but because the system moves air in a way that encourages natural, thorough mixing. Balanced airflow helps reduce hot and cold spots. Hot spots often arise when a space is poorly ventilated, when supply air fails to reach a certain area, or when local heat sources, a window, a piece of equipment, a group of people, overwhelm the airflow in that zone. Cold spots can form near exterior walls or in areas where supply air lingers without mixing. A well-balanced system accounts for these tendencies and delivers air in a way that minimizes them. And when the mixing is working well, the people in the room simply feel comfortable. They may not notice the air moving at all. There is no draft, no obvious temperature variation, no sudden shift in conditions. Only the steady, comfortable sense of a room that feels right. Not too warm, not too cool, stable, and easy to remain in. The supply air continues to enter the room, mix, and contribute to that stability. And as it does, it gradually becomes spent. It has given up its conditioning, or absorbed what it needed to from the room. It has done its work, and now it needs to make its way back to the system. The room air then moves toward return grills. At some point, the air that has mixed and settled and completed its role in the room finds its way toward the return openings. This happens naturally, guided by the gentle pressure differences that the HVAC system maintains throughout the building. Supply air comes in, return air goes out, and the room, balance between the two flows, maintains its comfort steadily and quietly. The transition from supply air to return air is seamless and unhurried. There is no single moment when one becomes the other. The room simply breathes, continuously and calmly, drawing in fresh, conditioned air and releasing used air back toward the system. And the mixing continues, as it always does, softly and without notice. The air has spent time in the room. It has mixed and settled. It has given up some of its conditioning, absorbing warmth in summer or releasing heat in winter. It has been breathed in and out by the people and systems around it. It has done what supply air is designed to do, and now it is ready to return. The room air then moves toward return grills. Return grills are the counterpart to supply diffusers. Where diffusers bring air in, return grills draw air out. They are usually positioned lower on walls or near the floor, though in some systems they may appear in ceilings as well. Their placement is intentional, chosen to encourage air to travel through the room in a natural and effective pattern before being drawn back into the system. Like diffusers, return grills are easy to overlook. They tend to be simple in design, metal or plastic faces with angled slats or a mesh pattern, offering little visual drama. But they serve a steady and important purpose. They are the beginning of the air's return journey, the moment when the room releases its air back to the system that delivered it. Return grills pull the air back into the system. The pull is gentle. It is created not by suction in any dramatic sense, but by the slight pressure difference that the HVAC system maintains. The supply air being pushed into the room creates a slight positive pressure. The return system, drawing air back out, balances that pressure. Air naturally flows from higher pressure toward lower pressure, and so the used room air drifts quietly toward the return grills without any forceful persuasion. You might imagine standing in a large, quiet office building late in the evening. The overhead lights are off. Only the emergency lighting casts a faint glow along the corridors. Somewhere near the base of a wall or along the ceiling of a hallway, a return grill sits in place, and through it, slowly and silently, the building's air is finding its way home. Return air often travels through return ducts. Just as supply air travels through supply ducts on its way to the room, return air travels through return ducts on its way back to the mechanical equipment. These ducts may be separate from the supply ductwork, running in parallel through the building's hidden spaces. Or in some systems, return air travels through open plenum spaces above drop ceilings, using the ceiling cavity itself as a large distributed return pathway. In either case, the movement is quiet and continuous. Return ducts help guide air back without disturbing the room. The return pathway is designed to collect air from many locations and bring it back toward the central equipment with minimal resistance. The ducts grow larger as they move toward the air handler, gathering contributions from multiple zones. Where supply ducts branch outward like the limbs of a tree, return ducts converge inward, drawing air from the edges of the building back toward its mechanical core. As the return air travels, it may pass through grills, around dampers, and through filters in some systems. It carries with it the accumulated warmth, humidity, and particles of the rooms it came from. It is not the same air that left the air handler. It has been changed by the space it occupied. And yet, it has value, because this air has already been conditioned. It has already been filtered and tempered. Returning it to the system means that not all the energy used to condition it needs to be used again. If the return air is close to the desired temperature, it requires far less heating or cooling than completely fresh outside air would need. The system can reuse it, recondition it, and send it back out with far less effort than starting from scratch. This is one of the quiet efficiencies built into the design of commercial HVAC systems. The return air loop reduces energy use and helps the system maintain comfort with less work. The return air continues its quiet journey inward. Through ducts and plenums and return grills, it makes its way back to the mechanical space, back toward the air handler, the filters, the coils, and the fans that will prepare it once again for its next cycle through the building. The loop is nearly complete. Air entered from outside. It was cleaned and conditioned. It traveled through ducts and VAV boxes and diffusers. It spent time in the room, mixing and serving its purpose. And now it is making its way back. The journey has been long and gentle and carefully guided at every step, and it is almost ready to begin again. The return air has made its way back to the mechanical space. It has traveled through grills and ducts, gathering from rooms and corridors and quietly converging toward the air handler. Now, at this central point in the system, a quiet decision is made. What happens to this air next? In most commercial HVAC systems, the return air does not simply go back into the building unchanged, nor is it entirely discarded. Instead, it becomes part of a carefully managed blend, mixed with fresh air from outside, reconditioned, and prepared to serve the building once more. Some return air is reused, while some is exhausted and replaced with fresh outdoor air. This balance between recirculation and fresh air intake is one of the fundamental design choices in commercial ventilation. Too much recirculation and indoor air quality can suffer. Stale air accumulates. Carbon dioxide levels rise as occupants breathe. Odors and humidity may build up without adequate dilution. But too much fresh, outside air means the system must work harder to condition it, since outdoor air arrives at whatever temperature the weather provides and must be brought to the proper indoor conditions before it can be useful. The system finds a balance. Some return air may be mixed with fresh outside air. That mixing happens at the air handler, where dampers control the proportions. Outside air dampers and return air dampers work together, opening and closing in coordinated ways to achieve the right blend. Building codes and ventilation standards often specify minimum quantities of fresh air that must be introduced per person or per square foot of occupied space. The system is designed to meet those minimums while also allowing for flexibility based on conditions. On a mild day, when outdoor air is close to the desired indoor temperature, the system may bring in more outside air than strictly required. This is sometimes called an economizer mode, and it allows the building to use the free cooling available from the outdoor environment without running mechanical refrigeration equipment. The result is the same comfortable indoor air, delivered with less energy. On a very hot or very cold day, the system reduces the amount of outside air it introduces, relying more on recirculated return air to minimize the conditioning load. Only the minimum required ventilation is brought in, and the rest of the airflow comes from within the building itself. This mix helps maintain ventilation. Ventilation is simply the process of exchanging indoor air with outdoor air. It dilutes pollutants, reduces humidity, and refreshes the indoor environment in ways that recirculation alone cannot. Fresh air helps rooms feel lighter and less stuffy. It reduces the buildup of carbon dioxide that naturally results from people breathing in an enclosed space. Fresh air can help a space feel lighter, even in the middle of the night. When a building may be largely unoccupied, some level of ventilation is typically maintained. The building's air is not left to grow stagnant. A small but steady introduction of outside air ensures that when people return in the morning, the indoor environment is fresh and ready. The system may send part of the air back through the air handler. The recirculated portion of the return air joins the fresh outside air and enters the air handler together. There, the blend is filtered and conditioned as one. The coils adjust the temperature, the fans maintain the pressure, and the combined air, now cleaned and brought to the desired conditions, is ready to begin the supply journey once again. Stale indoor air can be moved out of the building. Some of the return air is not recirculated. Instead, it is exhausted, pushed out of the building through dedicated exhaust systems. This is particularly important in areas where air quality concerns are highest, such as restrooms, kitchens, or spaces where chemicals or strong odors may be present. Exhausted air leaves the building and is replaced by a corresponding amount of fresh outside air, maintaining the pressure balance and ensuring proper ventilation. That loop helps keep the building comfortable in a steady way. In this sense, the air handling process is a kind of quiet metabolism. The building takes in what it needs from the outside world, uses what it can from what it already has, and releases what is no longer useful. It does this continuously, without interruption, in a rhythm that supports the health and comfort of everyone inside. The blend of return air and fresh air moves through the air handler once more. It is cleaned, it is conditioned, it is sent back out into the building, and the cycle, patient and continuous, begins again. There is something invisible at work throughout every corner of the building, something that cannot be seen and is rarely noticed by the people inside. And yet, it is fundamental to how air moves, how rooms feel, and how the entire HVAC system functions. That invisible force is pressure. Pressure balance helps the air move in the right direction. In a well-functioning commercial building, the air is always under slight, carefully managed pressure differences. Supply air is pushed into rooms at a slightly higher pressure. Return air moves back toward the system through a slightly lower pressure pathway. These differences are small, often only a fraction of an inch of water pressure, a measurement so slight that no person would ever feel it directly. And yet that gentle pressure gradient is what keeps the air moving in the right direction, continuously and without effort. Slight pressure differences guide air from supply to return. Think of it like a slow and steady current in a very calm river. The water does not rush, but it moves in a consistent direction because of a gentle gradient that runs from one end to the other. In a building, air behaves similarly. It moves from the supply openings toward the return grills because of the sustained, quiet pressure difference that the HVAC system maintains. This is why supply diffusers and return grills can be in the same room, and air will still move from one to the other in an organized way. The system does not rely on the air finding its own way randomly. It creates the conditions that encourage the right movement. Good pressure balance helps doors close smoothly and rooms feel stable. One of the most tangible effects of pressure balance is something people experience without thinking about it. A door that opens and closes without difficulty. A door that does not constantly try to push itself shut or swing open on its own. These behaviors, when they occur, are usually signs that pressure between two adjacent spaces has become unequal. Air is trying to move from an area of higher pressure to lower pressure, and it uses the gaps around the door frame to do so. When pressure balance is well maintained, doors behave as expected. They are not being pushed by invisible forces. They close with an even, smooth motion. The building simply feels stable and quiet. If pressure is out of balance, airflow can become uneven. Imbalanced pressure can cause a range of subtle problems. Air may flow from one zone into another in unintended ways. Hallways might feel drafty. Some rooms might receive too much supply air, while others receive too little. In sensitive environments like hospitals or laboratories, pressure imbalances can have more significant consequences, since these buildings often rely on carefully controlled airflow to prevent contamination from moving between spaces. For this reason, pressure balance is something that HVAC engineers think about carefully during design, and something that building operators monitor and adjust over time. It is not a fixed condition. It is a dynamic equilibrium, maintained continuously by the operation of the system. Properly set dampers help maintain that balance. Dampers throughout the duct system play a role in maintaining this equilibrium. By adjusting how much airflow goes to different areas, they help keep supply and return in proportion. A zone that receives too much supply air can be adjusted. A return pathway that draws too strongly can be balanced against its neighbors. The overall effect is a building in which air moves calmly and predictably from where it is delivered to where it is collected. Balanced pressure helps air move in the right directions. The result of all this careful management is a building that simply feels right to be in. Rooms are neither stuffy nor drafty. Corridors feel calm. Air quality is consistent from one area to another. The temperature holds steady. There are no mysterious cold drafts or inexplicable warm pockets. The pressure balance is doing its work quietly in the background. There is something worth pausing to appreciate in this idea. An entire building filled with air that is always moving, always under gentle pressure, always being guided toward balance. And yet, to the people walking through it, working in it, or resting within it, all of that invisible management simply feels like a comfortable room. A place that is easy to be in. A place where the air is fresh and the temperature is steady and nothing demands attention. A quiet system can still maintain pressure balance. Even in the middle of the night, when the building is largely empty and the HVAC system has reduced its output, the pressure relationships persist. Air still moves, still follows its gentle gradients, still makes its way from supply to return in an organized and deliberate way. The building breathes on a softer, slower rhythm, but it does not stop breathing. And in the still hours, with everyone else asleep, the pressure balance holds, invisible, patient, and steady. To understand how a large commercial building stays cool, it helps to think about what cooling actually means. Cooling does not create coldness, it moves heat. This is one of the foundational principles of refrigeration, and it shapes everything about how the cooling side of a commercial HVAC system is designed and operated. The system does not manufacture a cold substance and pump it into the building. Instead, it finds the heat that is inside the building and moves it carefully and continuously to somewhere outside. Refrigeration cycles move heat from inside the building to outside. The equipment that does this work at a large scale is called a chiller. Chillers are common in larger cooling systems. A chiller is, at its most fundamental, a machine that removes heat from water. That chilled water is then circulated through the building, passing through coils inside air handlers where it absorbs heat from the air. The now warmer water returns to the chiller, where the heat is removed again, and the cycle continues. The process by which the chiller removes heat involves a refrigerant, a fluid with particular physical properties that allow it to absorb and release heat efficiently as it changes between liquid and gas states. Inside the chiller, this refrigerant flows through a carefully controlled circuit. It absorbs heat from the building's water loop, evaporates into a gas, is compressed, releases its heat, and condenses back into a liquid, ready to absorb more. The cycle is continuous, precise, and largely invisible to anyone not standing directly beside the equipment. A chiller removes heat from water or refrigerant to support cooling. Chillers in commercial buildings can range from relatively modest units serving a single building to enormous machines capable of supporting an entire campus or complex. They tend to sit in mechanical rooms, on rooftops, or in dedicated plant spaces. Their presence is announced not by dramatic machinery noise, but by a steady mechanical hum, the sound of compressors and pumps working at a measured and consistent pace. But the chiller's work is only half of the cooling story, because once it has removed heat from the building's water, it must do something with that heat. It cannot simply hold it. It must release it somewhere. That somewhere is the cooling tower. Cooling towers help release heat to the outside air. A cooling tower is typically found on the roof of a commercial building, or sometimes at ground level nearby. It is designed to take the warm water that comes from the chiller's condenser side and release the heat it carries into the outdoor air. The process usually involves water flowing over fill material inside the tower while fans draw air through it. As the water and air contact each other, some of the water evaporates, and in doing so, it carries heat away with remarkable efficiency. The warm air, now carrying the heat from inside the building, rises out of the top of the cooling tower and disperses into the night sky. What was once the warmth of a conference room full of people, or the heat from dozens of computers, is released gently into the open air above the building. Cooling towers help dispose of heat outside the building. On a warm evening, if you were standing near a commercial building with a cooling tower operating above you, you might notice a faint mist rising from its top. That mist is the result of evaporation, the gentle sacrifice of a small amount of water that carries a great deal of heat away with it. The tower exhales this warm, humid air into the atmosphere, making room for the next cycle of cooling inside the building below. The combination of chiller and cooling tower forms a complete loop. The chiller absorbs heat from the building. The cooling tower releases that heat to the outdoors. Cooled water returns to the chiller to begin again. And the building remains comfortable, degree by quiet degree. Pumps move water through many commercial HVAC systems. Throughout this entire process, pumps are maintaining the circulation. They move chilled water from the chiller to the air handlers and back. They move condenser water from the chiller to the cooling tower and back. Their operation is steady and unhurried, maintaining the flow that makes heat transfer possible. The pumps do not draw attention to themselves. They simply turn, hour after hour, keeping water moving through the system's pipes and equipment with quiet persistence. And so the heat that entered the building as sunlight, as body warmth, as the output of electrical equipment finds its way out again, moves steadily from inside to outside, from the occupied spaces of the building to the open air above. The building stays cool. The equipment continues its patient work, and in the mechanical rooms and on the rooftops, the chillers and towers and pumps maintain their steady rhythm through the night. When the weather turns cold, the nature of the HVAC system's task changes. Instead of moving heat outward and away from the building, it must bring warmth in. It must gather energy and distribute it gently and steadily to every corner of the occupied space. The equipment at the center of this effort in many commercial buildings is the boiler. Boilers are common in larger heating systems. A boiler is a piece of equipment designed to heat water, or in some cases, to produce steam. That heated water is then circulated through the building, carrying its warmth to where it is needed. It passes through coils inside air handlers, transferring heat to the air moving across them. It may also flow through heating units near exterior walls or windows, adding warmth specifically to those areas most vulnerable to the cold outside. Heating starts by adding warmth where it is needed. The principle is simple, even if the execution involves considerable engineering. Water is heated by the boiler, pumped through the building's piping system, releases its heat in the places where it is needed, and returns to the boiler, somewhat cooler now, to be reheated and sent around again. The loop is continuous and gentle, maintaining a steady flow of warmth through the building's infrastructure. Boilers make hot water or steam for heating. In some systems, particularly older buildings or those with large heating demands, steam is used rather than hot water. Steam carries a great deal of thermal energy and can distribute heat efficiently across large areas. It rises naturally through pipes without needing pumps to push it, making it a self-moving heating medium in many configurations. As steam releases its heat and condenses back into water, it returns to the boiler to be converted to steam once more. Whether the system uses hot water or steam, the purpose is the same: to take energy and deliver it in a controlled and consistent way to the air and surfaces that will help maintain comfortable conditions inside the building. Coils transfer heat between air and water or refrigerant. In the air handler, the hot water or steam passes through coils that the air flows across. The coils are designed to maximize the transfer of heat from the water to the air, with metal fins that increase surface area and allow the exchange to happen efficiently. The air enters the coil section at the ambient temperature of the return air and leaves it warmer, ready to be distributed to the building's spaces. This heat exchange is quiet and consistent. The coils give up heat steadily. The air absorbs it steadily, and the air that leaves is gently warmed, carrying the boiler's contribution to every room it enters. Pumps move this water through pipes and equipment. Throughout the heating system, pumps maintain the circulation of hot water just as they do in the cooling system. They keep the water moving from the boiler to the coils and back, maintaining a steady flow that allows the heat transfer to continue without interruption. These pumps are often located in mechanical rooms, running quietly alongside the boilers and other equipment. Like so many parts of the HVAC system, the pumps are easy to overlook. They are not dramatic. They do not draw attention. They simply run, hour after hour, supporting the quiet work of keeping the building warm. Heat exchangers allow energy to move efficiently from one place to another. In some systems, heat exchangers separate the boiler water from the water that circulates through the building's air handlers. This can be useful for safety reasons or to allow different parts of the system to operate at different temperatures. One fluid gives up heat to another through a carefully engineered interface, and the energy moves across without the two fluids ever mixing. The result is still the same. Heat moves from where it is generated to where it is needed. On a cold night, with the temperature outside dropping and the building settling into darkness, the boiler continues its work. Water circulates through pipes that run behind walls and above ceilings. Coils in air handlers give up their warmth to the air that passes across them. VAV boxes deliver that warmed air into rooms where no one is present, but the building's systems have decided a minimum of warmth must still be maintained. A well-designed HVAC system supports comfort with little notice. The people who will return to this building in the morning will not think about the boiler. They will not consider the pumps or the coils or the piping that winds through the building's hidden spaces. They will simply find, when they arrive, that the building is warm, that their office is comfortable, that the hallways and common areas feel inviting rather than cold and unwelcoming. That is the quiet promise that heating systems keep, working through the night when no one is watching so that the building is ready when the morning comes. Running through the walls and beneath the floors of a large commercial building, hidden within shafts and ceiling spaces and mechanical rooms, is a network of pipes. These pipes carry water. Not all water is the same in an HVAC system. Some carries heat from boilers to coils. Some carries coolness from chillers to air handlers. Some carries the heat that has been removed from the building to the cooling towers above. And all of it is kept moving by pumps. Pumps move water through many commercial HVAC systems. Pumps are among the most reliable and unassuming pieces of equipment in the entire building. They do not transform anything. They do not change the temperature of the water or alter its chemical composition. They simply move it steadily and patiently from one point to another through the pipes that connect the building's various mechanical systems. Most commercial HVAC systems rely on several distinct water loops, each serving a specific purpose and each maintained by its own set of pumps. There is the chilled water loop, which carries water cooled by the chiller to the cooling coils in air handlers and fan coil units throughout the building. The chilled water absorbs heat from the air, passing across the coils, and then returns to the chiller, warmer than when it left, to be cooled again. There is the condenser water loop, which carries the heat removed by the chiller to the cooling tower, where it is released to the outdoor air. This loop closes the refrigeration cycle and allows the chiller to continue operating continuously. There is the hot water loop in buildings that use boilers for heating, which carries heated water from the boiler to heating coils and radiators throughout the building. The water gives up its heat and returns to the boiler cooler, ready to be reheated. Pumps move water through coils and mechanical equipment. Each loop has its own pumps, typically located near the central mechanical equipment, near the chiller, near the boiler, near the cooling tower. These pumps are sized to maintain the proper flow rate through their respective loops, pushing water at the speed needed to ensure adequate heat transfer at every coil along the way. In many systems, variable speed drives allow the pumps to adjust their output based on demand. When the building needs less cooling, the chilled water pumps may slow down, using less energy. When demand increases, they speed back up. This ability to modulate means the pumps are rarely running at full capacity, spending most of their time at a gentle, measured pace that matches exactly what the building requires. The pumps do their work quietly. This is perhaps one of their most important qualities. A well-maintained pump makes very little noise. It hums softly, or not at all from a distance. Water moves through pipes that are insulated against vibration. The mechanical energy of the pump is transferred almost entirely into the movement of water, with very little wasted as sound or heat. The result is a building in which the water systems operate almost undetected. Heat exchangers move heat efficiently from one place to another. At various points in the water loops, heat exchangers allow energy to pass between fluids without the fluids themselves mixing. A plate heat exchanger, for example, passes two fluids on opposite sides of a series of thin metal plates. Heat flows through the plates from the warmer fluid to the cooler one, transferring energy with high efficiency. These devices are compact, reliable, and operate with no moving parts of their own, relying entirely on the pumps to keep both fluids in motion. Regular maintenance helps the system run smoothly. Like all mechanical equipment, pumps and water systems benefit from consistent care. Pumps are checked for proper operation, their seals and bearings maintained or replaced as needed. Piping is inspected for proper insulation. Water treatment systems prevent the buildup of scale and biological growth inside the pipes and equipment. Clean, properly treated water moves more freely and transfers heat more efficiently than water that has become laden with mineral deposits. When maintenance is performed well, the water loops operate without interruption for years. The pumps turn, the water moves, the heat follows the path that has been designed for it, and the building maintains its comfort through the quiet, continuous work of these hidden systems. Imagine for a moment that you could see through the walls and ceilings of a large commercial building late at night. You would find a network of pipes stretching from basement to rooftop, from mechanical room to every occupied floor. Through those pipes, water moves steadily, driven by pumps that ask for no recognition, carrying heat toward where it is needed and away from where it is not. A quiet circulation, steady and patient, supporting everything. A large commercial building contains an enormous number of moving parts. Dampers open and close, fans speed up and slow down, pumps maintain their circulation, boilers and chillers respond to changing loads. VAV boxes adjust their output for dozens or hundreds of different zones. Thermostats across every floor send signals about current conditions. All of this happens simultaneously, continuously, and in coordination with each other. How does a building manage all of this at once? The answer is the building automation system. Building automation can coordinate many HVAC parts at once. A building automation system, sometimes called a BAS or building management system, is a network of sensors, controllers, and software that monitors and manages the operation of the building's mechanical and electrical systems. It is, in a sense, the nervous system of the building, constantly gathering information, interpreting it, and sending instructions to the equipment that keeps the building comfortable. Controls help the system respond calmly to changing conditions. Throughout the building, sensors measure temperature, humidity, airflow, carbon dioxide levels, and occupancy. Each of these measurements is collected and sent back to the building automation system, which compares the current conditions to the set points that have been programmed into it. If a room is too warm, the system directs its VAV box to open wider. If a zone is unoccupied, it may reduce airflow to that area. If outdoor conditions change, it adjusts the ratio of fresh air to return air accordingly. These responses are not reactive in a jerky or abrupt way. They are measured and deliberate, designed to maintain comfort without creating sudden shifts that would be noticed or felt by the people inside. A thermostat helps the system stay responsive, not rushed. Individual thermostats serve as local input points for the building automation system. A person adjusting a thermostat in a conference room is communicating a preference to the broader system. The BAS receives that input and begins working toward the new set point, adjusting the output of the VAV box and, where necessary, signaling upstream to the air handler and central plant that conditions in that zone have changed. The response travels back through the system in the same coordinated way. The chilled water pump may supply a bit more flow. The air handler fan may slightly increase its speed. The VAV box opens. The temperature in the conference room begins to drift toward the new target. All of this happens without anyone in the room lifting a second finger. Building controls can adjust the system throughout the day. Building automation systems are also programmed with schedules. They know when the building is typically occupied and when it is not. They anticipate the morning warm-up period before people arrive, bringing the building to a comfortable temperature before the first employees enter. They begin a gradual setback in the evening, easing the building's mechanical systems into a quieter mode as occupancy decreases. Zoned systems help different areas stay comfortable in different ways. Different parts of the building often have very different needs, and the automation system handles these differences simultaneously. A server room requires constant cooling, regardless of the time of day. A conference room may need maximum ventilation during a meeting, but reduced airflow in the hours before and after. Perimeter offices near large windows may require heating in the morning and cooling in the afternoon as the sun moves across the building. The automation system tracks all of these zones and responds to each of them in a way that is appropriate to that specific space. Sensors and controls quietly coordinate temperatures, airflow schedules, and equipment operation. There is something almost calming about the idea of a building automation system operating through the night. While the building is dark and quiet, while everyone inside is sleeping or gone, the system continues its gentle work. Sensors report, controllers interpret, equipment adjusts. The building does not truly sleep. It simply shifts into a quieter mode, one that preserves comfort and readiness while conserving energy and reducing wear on the equipment. And in the morning, when people return, the building is ready, comfortable, balanced, breathing at the pace that the automation system decided, through careful programming and continuous monitoring, was exactly what was needed. The building automation system never draws attention to itself. It operates without fanfare, responding to the needs of the building and the people within it. It is present in every thermostat signal, every damper adjustment, every fan speed change. And the result of all its quiet coordination is a building that simply feels right, steady, comfortable, well cared for. A commercial building is rarely a single uniform environment. From morning to night, from floor to floor, from a sun-drenched corner office to a windowless interior conference room, conditions are constantly shifting. People arrive and depart. The sun moves across the building's facade. Equipment generates heat. Meetings begin and end. And throughout all of this, the HVAC system responds, zone by zone, in a continuous effort to keep every part of the building comfortable. Zoning helps different areas stay comfortable in different ways. Zoning is the practice of dividing a building into distinct sections, each of which can be controlled somewhat independently. Rather than treating the entire building as a single space with a single temperature set point, a zoned system acknowledges that different areas have different needs, different heat loads, and different patterns of occupancy. A south-facing conference room in the afternoon sun has a very different cooling requirement than a north-facing office at the same time of day. A crowded break room at lunchtime needs more ventilation than it does at midnight. A data center tucked into the building's core needs continuous cooling, regardless of what the rest of the building is doing. Zoning allows the system to address each of these situations on its own terms. Occupied rooms usually need different airflow than empty rooms. This is perhaps the most fundamental principle of zoned operation. When a space is occupied, it typically needs more airflow to manage the heat generated by people and their equipment, and to maintain the fresh air required for good air quality. When a space is empty, those needs diminish considerably. A VAV box serving an unoccupied office may reduce its airflow to a minimum set point, enough to prevent stagnation, but far less than what would be needed during business hours. Across a building with many zones, this dynamic adjustment is happening constantly. Some zones are opening up as people arrive for the day. Others are modulating as conditions shift. Still others are quietly idling, maintaining minimal airflow in spaces that will not be occupied again until tomorrow. Building controls help everything work together. The building automation system coordinates all of these zone-level adjustments and ensures that they make sense in the context of the broader system. If several zones simultaneously call for more cooling, the system increases chilled water flow and adjusts the air handler output to meet the aggregate demand. If the building is gradually emptying out in the evening, the system scales back progressively, zone by zone, reducing the total load in a smooth and orderly way. Each zone receives only the airflow it needs, and conditions change gradually throughout the day. There is a rhythm to this that unfolds over the course of a typical building day. In the early morning before occupancy, the building automation system may begin warming or cooling the building back toward its occupied set points, preparing it for the people who will arrive. As occupancy increases, airflow and conditioning increase with it. At peak afternoon hours, the system may be working at its highest daytime capacity, managing a full building at the warmest part of the day. Then, as the afternoon fades and people begin to leave, the system begins to ease back. Zone by zone, floor by floor, the demand for conditioned air decreases. VAV boxes close partway. Air handlers reduce their output. The building gradually shifts from its daytime mode toward its nighttime mode, a transition that may take an hour or more and is entirely managed by the automation system. Balanced airflow helps reduce hot and cold spots. Even within a single zone, the goal is to deliver air in a way that creates even, consistent conditions throughout the space, not too warm in one corner and too cool in another, not stuffy near the center and drafty near the diffuser. The placement of diffusers, the volume of air delivered, and the configuration of the return system all work together to encourage thorough, even air distribution within each zone. Occupied rooms usually need different airflow than empty rooms. At night, the building settles into its quietest configuration. Most zones are at minimum airflow. The automation system maintains light oversight, ready to respond if conditions change unexpectedly, and the building, though largely empty, is not neglected. It is simply resting in the careful and deliberate way that a well-designed system allows. Tomorrow, the rhythm will begin again. The building will wake zone by zone as the automation system prepares it for another day. And the quiet, continuous work of maintaining comfort in a large and complex space will continue as it always does, in the steady and unhurried way that HVAC systems do everything they do. The last occupant has left the building. The elevator has made its final run of the evening. The lobby doors are locked, and the corridors are lit only by the quiet glow of emergency lighting. From the outside, the building looks still. From the inside, it is settling into a different kind of life. Quieter, slower, but no less cared for. At night, many buildings settle into a quieter operating mode. This is called a night setback, or sometimes a nighttime setback mode. The building automation system, following a schedule programmed into it, begins to shift the HVAC system toward lower output. Fans reduce their speed. VAV boxes close partway, delivering only a fraction of the airflow they maintained during occupied hours. Chillers may cycle less frequently or operate at reduced capacity. Boilers maintain water temperatures sufficient for protection against cold, but do not heat aggressively. The building breathes more slowly. Air still moves, but often at a lower pace. This is an important distinction. Night setback is not the same as shutting off the HVAC system entirely. The system continues to operate. Air continues to circulate. The pressure balance is still maintained. Fresh air is still introduced in modest quantities to keep the indoor environment from becoming completely stagnant. What changes is the intensity and scale of the system's operation. The set point temperatures are also adjusted. Instead of maintaining a precise 72 degrees for occupant comfort, the building may be allowed to drift to 76 or 77 degrees on a warm night or down to 68 degrees on a cool one. This expanded temperature range requires less mechanical effort to maintain and allows the system to run with less energy during the hours when no one is present to notice the difference. Low airflow at night can help the building rest while staying protected. The reduction in airflow has several benefits. Energy consumption drops, often significantly, since fans and compressors are the largest power consumers in the HVAC system. Equipment wear is reduced during the hours of lighter operation, and the building itself remains in a condition of gentle, continuous care rather than complete dormancy. Nighttime ventilation may continue in selected areas. Not every part of the building runs at reduced capacity during the night. Areas with continuous heat loads, server rooms, telecommunications closets, electrical switchgear rooms may require full or nearly full cooling regardless of the time of day. The building automation system knows about these zones and maintains appropriate conditions in them, even as it reduces airflow elsewhere. In some buildings, certain areas may actually see more activity at night than during the day. A hospital runs continuously. A data center generates heat without pause. An overnight cleaning crew moves through the building's spaces. The HVAC system adapts to these realities, maintaining comfort where it is needed and conserving energy where it is not. Gentle circulation helps prevent stale air from settling. Even in fully unoccupied spaces, a minimum level of airflow is often maintained. This gentle circulation keeps the indoor environment fresh enough that when people return in the morning, the air does not feel stale or heavy. It also helps prevent any temperature stratification, the tendency of warm air to rise and pool near ceilings while cooler air settles near the floor, from becoming pronounced. Cool or warm air may move slowly through the building. On a warm summer night, the chilled water system may continue circulating at reduced capacity, keeping the building from accumulating too much heat from solar gain and equipment loads even in the absence of occupants. On a cold winter night, the heating system maintains just enough warmth to protect pipes, equipment, and the building envelope from the effects of deep cold. Supply air may enter rooms in a soft, even way. The air that does move through the building at night does so with particular gentleness. Lower airflow means lower velocity in the ducts and at the diffusers. The air enters rooms more slowly and more quietly than it does during busy daytime hours. The sound of the system, already soft during normal operation, becomes even softer. A good nighttime system supports comfort without drawing attention. This is the defining quality of a well-designed night setback mode. It does enough and no more. It protects the building, maintains the indoor environment at a reasonable level, and positions the system to resume full operation efficiently in the morning, all without consuming more energy than necessary or making any more noise than is needed. The building continues, as it always does, patient, steady, breathing slowly in the dark. Deep within the building, away from windows and offices and corridors, there are rooms that most people never enter. Rooms where the building's machinery lives, where fans turn and pumps circulate and control panels hum with quiet purpose. These are the mechanical rooms, and at night they take on a particular quality of their own. Calm mechanical rooms often stay warm, orderly, and quiet. A mechanical room is a space set aside specifically for the equipment that serves the building. Air handlers, pumps, electrical panels, boilers, or chiller connections, piping systems, and controls may all be housed within these spaces. They are functional environments, designed for equipment access and maintenance rather than for human occupation. And yet there is something unexpectedly peaceful about a well-maintained mechanical room running smoothly through the night. The lights may be off when no technician is present. Only the status indicators on control panels cast a soft glow. A steady green light here, a slowly blinking amber there. The equipment makes sounds, but they are familiar and regular. The low hum of a fan, the periodic click of a relay, the soft rhythm of a pump in continuous operation. Well-designed equipment often sounds like a low background hum. This hum is the signature sound of mechanical equipment operating within its intended parameters. It is the sound of motors running smoothly, of bearings properly lubricated, of vibration properly isolated. When equipment is maintained well and sized correctly, its sound becomes almost like a background texture, present but unremarkable, reassuring rather than alarming. Fans may run slowly instead of at full speed. During nighttime setback, the large air handler fans that move air through the building are often operating at reduced speed. Variable frequency drives, devices that control the speed of electric motors, allow the fans to run at exactly the pace needed to maintain minimal airflow rather than always running at maximum capacity. At night, a fan that might spin rapidly during the afternoon may turn at only a fraction of that speed, producing a fraction of the noise and consuming a fraction of the energy. The result is an air handler that breathes softly rather than breathing deeply. Slow-moving air can feel gentle and unobtrusive. Even in the spaces where the air handler delivers its modest nighttime airflow, the effect is more like a whisper than a breath. Diffusers that might produce a faint, steady hiss during busy hours may be nearly inaudible at night. The pressure in the ductwork is lower. The air moves more slowly. The building itself is quieter, and the HVAC system adjusts to match. The HVAC system may keep a light watch over the building. Building automation systems continue their monitoring through the night, even as the mechanical output decreases. Sensors report. Controllers remain active. If a zone becomes too warm or too cold, the system notices and responds. If equipment develops an unusual condition, alarms are configured to notify maintenance personnel. The system does not sleep, even when the building is at its quietest. Some zones can be reduced, while others stay active. In the mechanical room itself, equipment that serves the entire building may continue at near normal levels, while equipment serving unoccupied zones operates minimally. A chiller that serves a server room may run steadily. A pump loop that serves a series of empty offices may circulate only enough water to maintain pipe temperatures and keep the system ready. The mechanical room holds all of these conditions simultaneously, serving each part of the building according to its need. Soft duct noise usually means airflow is smooth. One of the subtler signs of a well-running HVAC system at night is the character of the sound coming from the ductwork. Properly sized and installed ducts running at low nighttime airflow produce very little sound. Air moves through them without turbulence, without vibration. without the low rumble that can occur when systems are under stress or operating beyond their design parameters. The silence of the ducts is, in a way, a sign of health. Night operation may include only the air needed for safety and freshness. A mechanical room at night is a room in a state of measured readiness. Equipment that is not needed is at rest or at minimum load. Equipment that is needed runs steadily and quietly. The controls that coordinate everything remain alert, and the entire system waits, patiently and without strain, for the morning, when occupancy will return and the full capabilities of the system will once again be called upon. In a quiet building, HVAC often feels like a steady presence in the background. The mechanical room is where that presence lives, where it breathes and turns and circulates, where it does its work without audience or applause, through the long and peaceful hours of the night. There is a way of thinking about a large commercial building that goes beyond pipes and ducts and equipment, a way of seeing the building not as a collection of mechanical systems, but as something more unified, something that functions in certain ways like a living thing. Fresh air enters, conditioned air circulates, and return air flows back, like a slow and measured breath. This is the image that presents itself if you follow the air long enough. Outside, air drawn inward through louvers, cleaned and conditioned in the air handler, distributed through the branching network of ducts, like a circulatory system, to every occupied space, absorbed into the rooms, mixed, used, and then drawn back toward return grills and return ducts, making its way back to the center of the system. And then again. Fresh air in, conditioned air out, return air back, the cycle repeating without pause. A building breathes. The rhythm is slower than a human breath. A single, full cycle of air through a commercial building might take many minutes, even hours, depending on the size and design of the system. But the rhythm is there. Inhalation and exhalation, supply and return, outside and inside, a continuous exchange between the building and the world around it. Air moves quietly through the building. This movement, when you think about it, is extraordinary in its persistence. At every hour of every day, regardless of what is happening inside the building, regardless of whether people are present or absent, the air is in motion. It is never entirely still. The HVAC system ensures a continuous circulation, a constant gentle flow that prevents any space from becoming truly stagnant. Even in the deepest part of the night, when the building is empty and silent, the air is moving. Softly, slowly, but moving. A good HVAC system moves air almost unnoticed. The goal of this movement is to be imperceptible. The best HVAC systems are the ones that create comfort without being felt, without drafts, without temperature swings, without noise that draws attention. The air handler hums quietly in its mechanical room. The ducts carry air without vibration. The diffusers spread supply air so gently that no one sitting beneath them would feel a breeze. The building breathes, and those within it do not notice the breathing. They simply benefit from it. Air handlers help guide that air along. At the heart of the building's breathing is the air handler, the lungs, in this way of thinking about it. The air handler draws in, conditions, and expels. It is the mechanical engine of the breath cycle. Without it, The air would not move with purpose. It would not be filtered or conditioned or distributed. The building would cease to breathe in any meaningful sense. But with the air handler working steadily, the breath continues. Fresh air in, conditioned air out, return air back, hour after hour, day after day. Ventilation helps fresh air enter the building. This is the inhalation, the moment when the outside world and the inside world exchange something essential. Fresh outdoor air carries with it the qualities that make an indoor space feel alive. Lower carbon dioxide, the freshness of the world beyond the building's walls. The HVAC system brings this in deliberately in managed quantities and blends it with the building's recirculated air to create an indoor environment that feels clean and breathable. Return air flows gently back to the system. This is the exhalation, the air that has spent time in the building, absorbed its occupants' exhalations, picked up warmth and humidity and trace particles, makes its quiet way back toward the center. It does not resist. It follows the gentle pressure gradients the system has established. It returns. The building can feel still while the equipment continues working. Standing in a large, empty commercial building, late at night, you might feel that stillness, the silence of unoccupied corridors, the absence of human sounds. And yet beneath that stillness, if you listened carefully, you might notice a very faint presence. The distant hum of equipment, the almost imperceptible movement of air from a diffuser nearby, the gentle sense that the building is not truly asleep. It is breathing, quietly, steadily, with the same measured rhythm that it has maintained since the system was first turned on, and the first breath of outside air was drawn in through the louvers and set in motion through the long, careful journey that brings it, eventually, to every room in the building. The journey of air is often long, gentle, and carefully controlled. And in that journey, there is something worth appreciating. Something that speaks to the quiet care that goes into the design and operation of the systems that make large buildings livable. Every filter, every fan, every VAV box, every diffuser plays its part in a continuous, coordinated act of care, keeping the air fresh, the temperature steady, and the building in its own mechanical way alive. We have traveled a long way together tonight. We began outside in the still night air, watching as the building drew its first quiet breath through louvers set into its walls. We followed that air inward, through filters and air handlers, across coils that quietly changed its temperature, and into the long and branching network of ducts that carry it to every corner of the building. We watched as VAV boxes made their gentle adjustments, opening and closing in small, deliberate movements to give each space exactly the amount of air it needed. We saw supply air spread softly from diffusers, mixing with the room air in a slow and continuous exchange. We followed return air as it made its quiet journey back through grills and return ducts, completing the loop and beginning it again. We visited the mechanical rooms where chillers and boilers and pumps do their patient work. We considered the cooling towers releasing heat to the open air above the building. We traced the water loops that carry warmth and coolness through hidden pipes to every coil in every air handler. We listened for a moment to the soft hum of a pump running steadily through the night. We saw how sensors and controls coordinate all of these systems simultaneously, adjusting and responding without drama or urgency. We understood how zones allow different parts of the building to receive different care, and how the building shifts gradually and automatically from its busy daytime operation into the quieter rhythms of night. And throughout all of it, we followed the air. That quiet, continuous movement of air through a building is, in many ways, the story of everything we have discussed tonight. The HVAC system exists to move air, to clean it, to condition it, to distribute it, to collect it, and to send it around again. Every piece of equipment, every control, every duct and diffuser and damper is in service of that one simple goal. And it does this quietly. In a quiet building, HVAC often feels like a steady presence in the background. A good HVAC system does not announce itself. It does not intrude on the experience of the people inside. It simply maintains temperature, airflow, freshness, balance, with enough consistency that no one needs to think about it. The comfort it creates feels natural, as if the building simply exists in that state without any effort. But there is enormous effort behind it. There are pumps turning and fans spinning and coils exchanging heat and sensors reporting and controls adjusting and dampers moving. All of it happening at once, in coordination, in the background. The building is never truly still. Even now, in the quietest part of the night, somewhere above a ceiling or behind a wall, air is moving. A fan is turning at a slow and gentle pace. Water is flowing through pipes at a reduced but steady rate. A sensor is reporting that the temperature in an unoccupied corridor is exactly what it should be. And the building automation system, patient and watchful, notes the report and continues. HVAC often works quietly in the background. This is the great achievement of these systems. Not that they are complex, though they are. Not that they are efficient, though they can be, but that they are quiet. That they create comfort without requiring any conscious effort or attention from the people they serve. That a room can feel exactly right, day after day, without anyone inside it giving a single thought to how that came to be. Soft duct noise usually means airflow is smooth. If there is a sound at all, and often there is none, it is only the gentlest of sounds. A faint exhalation from a diffuser, a distant low-frequency hum from a mechanical room several floors away, the almost imperceptible whisper of air moving through a well-designed duct at minimal nighttime speed. These are not sounds that disturb. They are sounds that settle. They are the sounds of a building that is being cared for, a building that is breathing. A well-designed system helps people feel at ease. As you rest tonight, you can imagine that breathing continuing, the slow loop of air through a large and quiet building, the steady circulation of water through pipes in the walls, the gentle opening and closing of dampers responding to conditions that no one is awake to notice, the soft turning of fans maintaining a minimum pressure in an empty corridor. All of it continuing without you. All of it continuing for you. Because that is what HVAC systems are designed to do. They work in the background, always, so that when you enter a space, it simply feels right. So that when you sit at a desk, or walk through a hallway, or rest in a room, you are comfortable. The temperature is steady. The air is fresh. The space is balanced. You do not need to think about any of it. You only need to be here. And so, as this long and gentle journey through the systems of a building comes to its quiet end, you can let the sound of it drift away. The ducts and diffusers and dampers and coils and pumps and fans, all of it fading into the background as it always was meant to be. The building breathes, slowly, steadily, and so can you.